Have you ever gazed up at the night sky, watching those countless pinpricks of light scattered across the darkness, and wondered if there's more connecting them than just empty space? What if I told you that the universe might be whispering secrets to itself across unimaginable distances, secrets that defy everything we thought we knew about reality? Picture this: two galaxies separated by billions of light years, somehow influencing each other instantly, as if bound by an invisible thread stretching across the cosmos. This isn't science fiction. This is the breathtaking frontier of quantum entanglement operating at scales so vast, it challenges our very understanding of existence. For decades, quantum entanglement has fascinated scientists as a strange, almost magical phenomenon where particles become linked in such a way that the state of one instantly affects the other, no matter how far apart they are. But what if this connection isn't limited to tiny particles in a lab? Imagine entanglement weaving through the fabric of the universe itself, tying together stars, galaxies, and even the fate of cosmic structures in a web of instantaneous communication. It sounds like something straight out of a futuristic tale, yet cutting-edge research is now suggesting that quantum effects might be at play on the largest scales imaginable, shaping the universe in ways we're only beginning to grasp. Today, we're embarking on a journey to explore one of the most profound ideas in modern physics: the possibility that entanglement isn't just a quirky quantum oddity, but a fundamental force orchestrating the cosmos. We'll dive into how scientists are uncovering clues that the universe might be far more interconnected than we ever dreamed, and what this could mean for everything from the birth of galaxies to the ultimate fate of reality itself. This is a story of human curiosity, of pushing the boundaries of knowledge, and of daring to ask questions that once seemed impossible. So join me as we unravel the mysteries of entangled galaxies and step into a new understanding of the universe, one where the lines between the infinitely small and the impossibly large blur into something truly extraordinary. To grasp how something so bizarre could operate on a cosmic scale, we first need to understand the basics of this quantum connection. At its heart, quantum entanglement is a relationship, a shared existence between particles. Think of it not as two separate things sending a signal, but as a single system described by one shared quantum state. It's like creating a pair of magical dice. You roll them together, and no matter what, they always land on the same number. Now, imagine taking one of those dice and launching it to the farthest star in the universe. The instant you look at the die you kept here on Earth and see it landed on a 3, you know with absolute certainty that its distant partner also shows a 3. This connection isn't a beam of light or a radio wave traveling through space. The information is shared instantly, transcending the vast distance between them. This spooky action at a distance, as Einstein famously called it, baffled physicists for generations because it seems to break the universe's ultimate speed limit, the speed of light. The key to this mystery is that the particles aren't truly communicating in the way we normally think. It's more accurate to say their fates were intertwined from the moment they were created. Their properties, like spin or polarization, weren't predetermined. They existed in a fuzzy cloud of potential, a superposition of all possible states, and it's only at the moment of measurement that their shared state collapses into a definite, correlated outcome. This isn't just a theoretical curiosity, it's a proven fact of our universe, demonstrated repeatedly in laboratories around the world. Scientists have entangled particles and confirmed their linked behavior over distances of hundreds of miles. But this leads to a monumental, awe-inspiring question. If this can happen for particles here on Earth, what's to stop nature from weaving the same invisible threads between objects on a much, much larger scale? Could the fundamental building blocks of reality, this strange quantum connectedness, be a feature not just of the microscopic world but of the cosmos itself? This profound disconnect between the quantum and cosmic realms forms one of the biggest puzzles in all of physics. For over a century, we've operated under a fundamental assumption: the universe is divided. In one corner, we have the quantum world, a bizarre and probabilistic domain where particles can be in two places at once and communicate instantaneously across space. This world is ruled by the precise yet strange laws of quantum mechanics. In the other corner, we have the grand, majestic arena of galaxies, stars, and planets, the cosmos. This world appears to run like a perfect, predictable clockwork, governed entirely by the force of gravity as described by Einstein's theory of general relativity. These two sets of rules, quantum mechanics and general relativity, are both spectacularly successful in their own domains, but they speak completely different mathematical languages and have proven stubbornly incompatible. The core of the problem lies in scale. Quantum weirdness thrives in the small. We can observe and even manipulate entanglement in the lab because we can isolate pairs of particles or atoms, protecting their delicate quantum state from the outside world. But scale that up and a phenomenon called decoherence kicks in. Think of it like trying to hear a whisper in a roaring hurricane. The quantum whisper, the subtle, interconnected state of a particle, is easily drowned out by the constant, crashing noise of the environment. A single photon from a distant star, a random molecule of air, or even the faint warmth of a surface is enough to disrupt and destroy these fragile quantum connections. This is why, in our everyday, warm and bustling macroscopic world, we don't see cats being both alive and dead or footballs existing in two goalposts at the same time. The quantum weirdness gets averaged out, leaving us with the familiar, definite reality we experience. This is precisely why the concept of entangled galaxies is so revolutionary and, to many, so controversial. It directly challenges this long-held boundary. A galaxy isn't a lone, isolated photon in a vacuum chamber. It's an almost unimaginably vast collection of hundreds of billions of stars, swirling clouds of gas and dust, dark matter, and countless particles, all constantly interacting in a chaotic cosmic dance. According to our traditional understanding, the quantum state of an entire galaxy should decohere instantly. Its components are constantly measuring each other, collapsing any potential for large-scale quantum behavior almost as soon as it could form. To suggest that galaxies could be quantum entangled is to suggest that this decoherence, this foundational principle, might not be the final word. It proposes that under certain extreme conditions, perhaps in the pristine emptiness of the intergalactic void or woven into the fabric of space-time itself, quantum connections could be preserved or even generated on a scale that defies intuition. This idea pushes at the very limits of our theories and forces physicists to ask uncomfortable yet thrilling questions. Are we missing a deeper principle that unites the quantum and the cosmic? Could entanglement be not just a feature of particles but a fundamental property of space-time, meaning the universe itself is built upon a network of quantum connections? The controversy isn't about the mathematics being wrong. It's about our paradigm of how the universe operates being perhaps incomplete. Embracing the possibility of entangled galaxies means being open to a universe that is far more deeply and strangely interconnected than we ever believed possible. It was Albert Einstein himself, one of the founding fathers of quantum theory, who initially found the idea of entanglement so deeply unsettling. In the 1930s, as the new science of quantum mechanics was taking shape, Einstein saw a fundamental problem. He, along with physicists Boris Podolsky and Nathan Rosen, devised a clever thought experiment, now known as the EPR paradox, to highlight what they saw as a flaw in the theory. They argued that if quantum mechanics were a complete description of reality, then it would allow for what Einstein famously dubbed spooky action at a distance, this instant connection between particles separated by vast stretches of space. To Einstein, this was impossible. It violated the central tenet of his own theory of relativity, which stated that no information or influence could travel faster than the speed of light. He believed this spooky action revealed that quantum mechanics was an incomplete theory, that there must be some hidden variables, some deeper layer of reality we hadn't yet discovered, that would determine the properties of particles from the moment they were created and restore a sensible, local universe where influences couldn't leap across space instantly. For decades, this remained a philosophical debate, a battle of ideas fought on paper with equations and thought experiments. How could you possibly test something so abstract? Then, in the 1960s, a brilliant physicist named John Stuart Bell entered the stage. Bell, working largely outside the mainstream of quantum research, formulated a mathematical theorem that would change everything. Bell's theorem provided a way to translate this philosophical argument into a real, measurable experiment. It created a precise test, a threshold that any local, hidden variable theory, the kind Einstein hoped for, would have to obey. If the results of a certain measurement exceeded this threshold, it would mean that Einstein was wrong and that the spooky action was real. The wait for technology to catch up to Bell's ingenuity was long, but in the 1970s and 80s, a series of pioneering experiments, most notably by Alain Aspect and his team in France, finally put it to the test. They created pairs of entangled photons and measured their properties in different directions over increasing distances. The results were unequivocal. Again and again, the measurements violated Bell's inequality, smashing through the threshold that any local universe would allow. The particles were correlated in ways that simply could not be explained by any predetermined hidden variables or any signal traveling between them at the speed of light. The universe had chosen spookiness. It was a monumental moment in physics, not because it proved Einstein wrong about everything, but because it proved the universe was far stranger than even he could have imagined. The weirdness wasn't a bug in quantum mechanics, it was a feature of our reality. This experimental validation transformed entanglement from a theoretical curiosity into a concrete, physical phenomenon. It became something you could not just ponder, but actually hold, measure, and use. This shift laid the essential groundwork for everything that followed, including the audacious idea that these quantum links might not be confined to our laboratories. If nature permits this instantaneous connection for particles we create, could it also be forging these bonds on its own on a cosmic scale? The experiments that defeated Einstein's objections didn't just win an academic debate, they opened a door. They gave us the confidence to look up at the night sky and ask if the same quantum rules governing particles in a lab might also be silently at work, weaving the vast tapestry of the cosmos together in a web of spooky connection. The journey from a baffling thought experiment to a proven fact of nature required more than just brilliant ideas. It demanded ingenious technology. After Bell's theorem provided the blueprint, scientists embarked on a race to test it, pushing the limits of distance and precision. Early experiments in the 1970s and 80s were confined to cramped laboratory basements, with entangled particles separated by mere meters. Alain Aspect's groundbreaking work used delicate lasers and crystal setups to generate photon pairs, sending them down different paths to detectors just a few meters apart. The results were clear and repeatable. The particles remained linked, their fates intertwined in a way that defied any classical explanation. But a nagging question remained for the most skeptical critics. Could there be some unknown, subluminal communication, some hidden signal traveling at, but not exceeding, the speed of light, that was secretly coordinating the particles' behavior in these short-distance experiments? To truly slam the door on this possibility, researchers realized they had to separate their particles so far apart that not even a light-speed signal could connect them in the time it took to make a measurement. This launched a new era of long-distance entanglement experiments. Scientists began using fiber optic cables snaking through cities and under mountains. Teams in Vienna and Geneva achieved separations of over 100 kilometers, timing their measurements with exquisite precision. they would generate an entangled pair, send one photon zipping through a glass fiber, and then perform measurements at both ends simultaneously. The outcome was always the same. The correlation held strong, even when the particles were so far apart that a light signal would have taken microseconds to travel between them, and the measurement was completed in nanoseconds. The connection was instantaneous. Any hope of a hidden, light-speed signal being the culprit was completely eliminated. But the ultimate laboratory for testing quantum mechanics wasn't on Earth, it was in space. The atmosphere, while clear, absorbs and scatters the delicate photons needed for these experiments, placing a hard limit on distance for ground-based systems. The solution: take the experiment off-planet. This ambition culminated in projects like China's MISHA satellite, a quantum science laboratory launched into orbit. This pioneering mission performed a series of breathtaking experiments. It could generate pairs of entangled photons on the satellite and then beam them down to two separate ground stations on Earth, each separated by over 1,200 kilometers, a distance far greater than any fiber optic link could manage without catastrophic signal loss. The process was a marvel of engineering and timing. The satellite, moving at over 17,000 miles per hour, had to precisely target its entangled photons to receiving telescopes in different cities, all while battling atmospheric turbulence. And yet, it worked flawlessly. The results, published in leading scientific journals, showed that quantum entanglement held firm even over intercontinental distances. The satellite wasn't just a technological triumph, it was a profound philosophical statement. It demonstrated that this quantum connection is a robust and scalable feature of our universe, not an artifact of small-scale laboratory conditions. It proved that we can create and maintain these spooky links on a truly planetary scale. This progression from a meter-wide tabletop to a satellite linking continents is what makes the next logical step so compelling. If we can actively create and preserve entanglement over 1,000 kilometers with our own technology, what might the universe, with its 14 billion years of existence and unimaginable energy, have accomplished? The laboratory proofs show us that the phenomenon itself is not limited by distance. The only thing that ever stands in its way is decoherence, the disruptive noise of the environment. So we are left with a thrilling new question. Are there places in the cosmos, environments so vast and quiet and cold, that they could naturally protect quantum states on a scale we are only beginning to envision? The success of our own experiments doesn't just confirm a theory, it invites us to look up and wonder if the stars themselves are dancing to a quantum tune. This leap from the controlled environment of a laboratory to the wild, untamed cosmos requires a new way of thinking, a bridge between the quantum and the cosmological. The key lies in some of the most ambitious and speculative theories in modern physics, ideas that attempt to finally unite quantum mechanics with general relativity. One of the most promising avenues is the concept of quantum gravity. For decades, physicists have struggled to describe gravity, the force that shapes galaxies and bends space-time using the language of quantum mechanics. The leading candidate for this theory of everything is string theory, which proposes that the fundamental building blocks of the universe are not point-like particles but incredibly tiny, vibrating strings. And one of the most profound revelations from this line of thinking is that entanglement might not just happen within space-time, it might actually be what creates the fabric of space-time itself. Imagine the universe not as a static stage on which particles perform, but as a dynamic, woven tapestry. Each thread in this tapestry represents a quantum connection between particles. Now, weave billions upon billions of these threads together, creating a dense, interconnected network. According to this radical view, the very geometry of space-time, its smoothness, its curvature, its existence emerges from this underlying web of quantum entanglement. It's a concept that turns our intuition inside out. We normally think of two objects being entangled because they are close together in space. but this new perspective suggests they are close together in space because they are entangled. The distance between 2 points might be, at its most fundamental level, a measure of how entangled they are. The more entangled two systems are, the shorter the effective distance between them in the emergent spacetime. This provides a stunningly elegant mechanism for how entanglement could operate on a galactic scale. It might be the very glue that holds the architecture of the universe together. This idea finds support in another groundbreaking concept, the ER equals EPR conjecture proposed by physicists Juan Maldaisner and Leonard Susskind. This deceptively simple equation is a work of profound genius. It proposes a direct link between two of physics' greatest puzzles. ER refers to an Einstein-Rosen bridge, which is the formal name for a wormhole, a theoretical shortcut through spacetime. EPR, of course, refers to the Einstein-Podolsky-Rosen paradox, the very thought experiment that highlighted the strangeness of quantum entanglement. The conjecture boldly states that these two seemingly unrelated phenomena are actually two sides of the same coin. A wormhole, a tunnel through the fabric of the universe, is equivalent to a pair of entangled particles. Think about that for a moment. The spooky action at a distance that so troubled Einstein might not be action across a vast emptiness at all. Instead, what appears to be an instantaneous connection between two separated particles could actually be a communication through a microscopic wormhole, a hidden bridge in the geometry of spacetime that connects them. This doesn't violate the speed of light because the information isn't traveling across space. It's taking a topological shortcut through it, while a wormhole connecting two individual particles is unimaginably tiny. The principle could scale up. If entanglement can create a wormhole, could a sufficiently vast and complex web of entanglement create the cosmic structures we see? Could the gravitational pull that binds a galaxy together, or the mysterious dark energy pushing galaxies apart, have their origins in the ebb and flow of quantum information flowing through an unseen network of connections? These are not just poetic metaphors, they are serious proposals with mathematical backing, pushing us to consider that the universe's largest structures and its smallest phenomena are inextricably linked. The void between galaxies may not be empty and inert, but thrumming with quantum potential, a foundational layer of reality where entanglement quietly sculpts the cosmos. Now, let's turn our gaze to one of the most enduring puzzles in all of modern cosmology, the mystery of dark matter. We've observed for decades that galaxies don't rotate the way they should. The stars on the outer edges of spiral galaxies are whipping around so fast that the visible matter, all the stars, gas, and dust we can see, shouldn't provide enough gravitational glue to hold them in place. According to the laws of gravity, these galaxies should have flown apart eons ago. The prevailing explanation is that they are embedded within vast, massive halos of an invisible substance that we cannot see or directly detect, a substance we call dark matter. This mysterious stuff is thought to make up about 85% of all the matter in the universe, yet its true nature remains one of science's greatest enigmas. But what if we've been thinking about this problem from only one angle? What if the strange behavior of galaxies isn't solely due to an unseen form of matter, but is also a signature of an unseen form of connection? This is where our journey into quantum entanglement takes a fascinating turn. Could the spooky links between particles operating on a cosmic scale contribute to the effects we attribute to dark matter? It's a radical idea, but let's break it down. Remember the concept that entanglement might be fundamental to the very fabric of spacetime. If the universe is indeed a network of quantum connections, then the distribution of this entanglement is not necessarily uniform. Some regions of space could be more densely woven with these quantum threads than others. This intricate tapestry of connections could subtly alter the geometry of spacetime itself, creating an additional gravitational effect that we, from our classical perspective, have misinterpreted as the gravitational pull of invisible matter. Think of it like this. Imagine a perfectly flat, taut bed sheet representing empty space. If you place a heavy object in the center, it creates a deep depression. That's the gravity from normal matter. Now imagine that the fabric of that sheet isn't perfectly smooth. It's subtly textured or puckered in a wide area around the center. This texture adds a slight, extra curvature to the entire region, altering how objects roll around the central depression. From a distance, it would look as if there's more mass present than there actually is, because the overall shape of the sheet is more warped. In this analogy, the texture of the sheet represents a background level of large-scale quantum entanglement. This pervasive connectivity could be providing that extra curvature, that additional gravitational influence that perfectly explains why stars on the outskirts of a galaxy orbit faster than expected, without requiring vast amounts of invisible particles. This perspective doesn't necessarily seek to completely replace the concept of dark matter, but rather to expand our understanding of its potential nature. Perhaps dark matter isn't just a cloud of exotic particles passing through us. Perhaps it is also a manifestation of the universe's intrinsic quantum connectivity, a property of space-time itself that becomes significant on galactic scales. This idea is still very much on the frontier of theoretical physics, but it showcases the incredible power of thinking differently. By daring to apply the rules of the quantum world to the largest structures we know, we might finally be piecing together a more complete and astonishing picture of the cosmos, one where the invisible threads of entanglement are silently guiding the dance of the galaxies. Yet the story of cosmic connectedness doesn't end with the hidden scaffolding of dark matter. It weaves itself into an even deeper and more expansive mystery, the baffling force known as dark energy. For the past 2 decades, astronomers have made a discovery so shocking it has reshaped our entire cosmic narrative. The expansion of the universe isn't slowing down, as everyone expected from the relentless pull of gravity. Instead, it's accelerating. Galaxies are flying away from each other faster and faster, as if some invisible, repulsive force is stretching the very fabric of space-time itself. This mysterious driver of cosmic acceleration is what we call dark energy, and it makes up a staggering 68% of all the energy in the universe. But its origin is a complete enigma. What if the key to understanding this immense pushing force lies not in some exotic new field, but in the inherent energy of empty space itself, a vacuum humming with quantum activity that might be deeply, fundamentally entangled? To grasp this, we must first reimagine what we mean by nothing. The quantum vacuum is not a true nothingness. It is a seething, bubbling sea of potential, where virtual particles constantly flicker in and out of existence, borrowing energy from the universe for the briefest moments before vanishing again. This endless dance creates a background energy that permeates every cubic centimeter of space, a phenomenon known as vacuum energy. According to the rules of quantum mechanics, this energy should have a gravitational effect. The problem is, when physicists try to calculate how much energy this quantum vacuum should contain, their theoretical predictions are catastrophically wrong. They arrive at a number that is off by a factor of 10 to the power of 120. That's a 1 followed by 120 zeros. It is arguably the worst prediction in the entire history of science. This colossal discrepancy is known as the cosmological constant problem. This is where entanglement offers a potentially revolutionary perspective. What if the vacuum energy isn't just a random, chaotic froth, but is instead structured and organized by quantum entanglement on a cosmic scale? Imagine the vacuum not as a stormy sea of isolated particles, but as a vast, interconnected network. In this view, the virtual particles popping in and out of existence aren't acting alone. They are entangled with each other across vast distances. This long-range connectivity could impose a kind of order on the chaos. effectively suppressing the wild fluctuations and preventing the vacuum energy from reaching those unimaginably high levels predicted by naive calculations. The entanglement woven into the fabric of spacetime itself could be acting as a regulator, fine-tuning the vacuum's energy to the much lower, but still significant value that we observe as dark energy. In this scenario, dark energy isn't caused by the vacuum's energy alone, but by the specific, entangled nature of that vacuum energy. The profound implications of this idea ripple outward, affecting the very dynamics of galaxies. We already discussed how entanglement might contribute to the dark matter halo effect, but its potential role as dark energy adds another layer of cosmic influence. This isn't two separate phenomena. It could be two different manifestations of the same underlying quantum reality. The same web of entanglement that provides the extra gravitational curvature we attribute to dark matter could also be responsible for the energy causing the accelerated expansion. The universe's quantum connectedness might therefore be engaged in a grand cosmic balancing act, a gentle tug of war on the largest scales. On the level of a single galaxy, the entangled vacuum might enhance gravity, helping to bind stars together. But on the intergalactic scale, across the mind-boggling voids between clusters of galaxies, the cumulative effect of this pervasive vacuum energy wins out, pushing everything apart and driving the acceleration of the universe's expansion. This paints a picture of a cosmos that is truly holistic and deeply unified, where the same fundamental quantum principle governs both the clumping of matter and the stretching of space. The entangled vacuum becomes the central character in the cosmic story, a hidden actor whose interconnected nature simultaneously sculpts the galaxies and dictates the ultimate fate of everything. It suggests that the answers to our biggest cosmological questions may not be found by discovering new particles, but by understanding the intricate and invisible relationships between the ones we already have. The void of space, it turns out, might be the most interesting and active place of all. So if this grand vision of a quantum-woven cosmos is more than just a beautiful theory, where might we actually look for its fingerprints? The answer may lie in the heavens themselves, in the silent, synchronized dance of entire families of galaxies. For decades, astronomers have been meticulously mapping the universe, and in this vast catalogue of cosmic structures, they've begun to notice something peculiar. When they observe colossal clusters of galaxies, gravitationally bound cities containing thousands of individual galaxies, they sometimes find patterns that are strangely coordinated. It's as if these island universes, separated by millions of light-years of emptiness, are moving to the beat of the same hidden drum. These aren't just random alignments, they are correlations in their properties, their orientations, and even their rates of star formation that seem to defy a simple, local explanation. Consider a specific head-scratching example. Astronomers have found pairs of galaxies, or even small groups, that appear to be aligned in their rotation or the orientation of their central supermassive black holes in ways that are statistically very unlikely to occur by pure chance. In a classical cause and effect universe where influences are limited by the speed of light, this makes little sense. If two galaxies are 100 million light-years apart, any signal or force that could possibly coordinate their behavior would take 100 million years to travel between them. For them to appear synchronized today, that coordinating signal would have had to be sent in the distant past, long before the galaxies even existed in their current forms. It's a chronological impossibility that points toward a different kind of connection, one that operates outside the conventional bounds of space and time. This is precisely where the quantum perspective offers a breathtaking alternative. What if these correlated galaxies aren't communicating across space? What if, in a sense, they were never truly separate to begin with? The phenomenon of quantum entanglement provides a ready-made mechanism for this kind of instant, non-local correlation. We know it works for particles. The laboratory proofs are undeniable. the radical proposition is that the same principle could be preserved or generated on a galactic scale. Perhaps these galaxies share a common origin, emerging from the same primordial patch of the early universe. Their constituent particles could have been quantum entangled in that fiery birth, and despite being flung far apart by the expansion of the cosmos, that deep, fundamental connection remained. Their synchronized properties wouldn't be the result of a signal sent between them, but the enduring expression of a shared quantum state that has persisted for billions of years. This idea pushes the limits of what we believe is possible, given the constant threat of decoherence. But perhaps the extreme environments of the cosmos provide a sanctuary for quantum effects. The near-perfect vacuum of intergalactic space is the coldest, quietest, and most isolated environment imaginable. There are far fewer particles to crash into and disrupt a delicate quantum state than there are in our warm, noisy labs on Earth. Furthermore, the immense gravitational fields of galaxy clusters and the dark matter halos that surround them could act as a protective cocoon, shielding large-scale quantum correlations from decoherence. It's a compelling thought that the very things we are trying to explain, the dark matter and the gravitational anomalies, might themselves be the very mechanisms that allow these quantum connections to flourish on such an unimaginable scale. Of course, the scientific community approaches these observations with healthy skepticism. Correlation does not always equal causation, and astronomers are diligently working on alternative, classical explanations. Perhaps these alignments are remnants of the universe's large-scale structure, vast cosmic filaments of dark matter that guided the formation of galaxies along similar paths, giving them a common spin. This would be a local, if incredibly vast, gravitational explanation. The challenge for the quantum hypothesis is to find a smoking gun, a specific signature that cannot be replicated by any classical gravity model. This might involve discovering correlations that are simply too perfect, too instantaneous, or involve properties that gravity cannot influence, like the specific quantum spin states of matter across different galaxies. The search for this evidence is now a driving force in observational cosmology. New telescopes, both on the ground and in space, are collecting data on millions of galaxies with unprecedented precision. Researchers are developing sophisticated statistical tools to scour this data for these anomalous correlations, looking for the subtle but definitive marks of quantum connectedness written across the sky. They are essentially treating the cosmos as the ultimate quantum laboratory, one that has been running an experiment for 14 billion years. The synchronized dance of galaxy clusters may be more than just a cosmic curiosity. It could be the first visible tremor of a deeper quantum reality, a faint echo from the entangled foundations of the universe itself, inviting us to listen. To venture even deeper into this cosmic mystery, we must explore one of the most mind-bending concepts in theoretical physics, the holographic principle. This idea suggests that our perception of a three-dimensional universe filled with volume and depth might be an illusion, a magnificent projection of information encoded on a distant, two-dimensional surface. Think of it like a hologram on your credit card. That seemingly three-dimensional image isn't actually deep. It's generated from a flat, two-dimensional film. Now, scale that up to encompass the entire cosmos. The holographic principle proposes that everything we see and experience, every galaxy, every star, every person, could be akin to a cosmic movie projected from the information stored on the boundary of the universe. It's a staggering notion that redefines reality itself, and right at the heart of this projection, acting as the essential glue, is quantum entanglement. The connection between this principle and the entangled galaxies we've been discussing is profound. For a hologram to work, for a two-dimensional surface to perfectly encode all the information needed to project a flawless three-dimensional reality, every single point in that 3D space must be linked to the information on the 2D surface. There can be no loose ends. The entire system must be inextricably connected. This is where entanglement becomes absolutely crucial. It provides the mechanism for that connection. The vast, complex web of quantum entanglement between the fundamental units of information on the boundary is what creates the coherence, the structure, and the very appearance of the three-dimensional universe we inhabit. In this view, entanglement isn't just a feature of the universe, it is the very thread that weaves the holographic tapestry. This leads to an astonishing implication for our understanding of galaxies. If the holographic principle is correct, then two galaxies that appear separated by 1 billion light-years of three-dimensional space are not truly distant from each other in the fundamental description of reality. At the foundational level, on that two-dimensional boundary, the information describing those two galaxies could be right next to each other, entangled in an intimate dance. Their apparent separation in our 3D projection is just that, an appearance, a consequence of how the hologram is decoded. Their instantaneous quantum correlation, which seems so spooky from our 3D perspective, becomes perfectly natural from the 2D viewpoint. They are linked because their source codes are neighbors. We can push this analogy even further with a more relatable example. Consider a video conference call. You see the faces of your colleagues in three-dimensional boxes on your two-dimensional computer screen. From your perspective on the screen, their images are separate. But at the server level, the data packets containing their video streams are all jumbled together, processed, and intertwined. The seamless experience you have is built upon a hidden layer of complex connections and data transfers that you never see. The holographic universe might operate in a similar way. The 3D reality we perceive is the user interface, while the real work, the storage and processing of information, happens on a deeper, two-dimensional layer where entanglement is the primary language of communication. This perspective offers a radical new way to interpret the synchronized galaxies and the mysteries of dark energy. The strange correlations between distant galaxies might be the cosmic equivalent of a software glitch, a place where the underlying code of the hologram becomes faintly visible, revealing that two seemingly independent objects are, in fact, reading from the same data segment on the boundary. The accelerated expansion of the universe, driven by dark energy, could be understood not as a force within space, but as a thermodynamic process on that distant two-dimensional surface, like a memory bank cooling down and increasing in entropy. The holographic principle, powered by entanglement, doesn't just suggest that the universe is connected. It proposes that our entire experience of reality is a shared dynamic projection, a story written in quantum links on the edge of everything we know. But to find the ultimate testing ground for these ideas, we must journey to the most extreme environments in the universe, the enigmatic depths of black holes. These cosmic monsters, where gravity is so intense that not even light can escape, have long been the site of physics' greatest paradoxes. And right at the heart of the most famous of these, the black hole information paradox, we find quantum entanglement playing a starring role, with implications that could ripple out to affect entire galaxies. The story begins with Stephen Hawking's revolutionary discovery in the 1970s. Hawking realized that black holes aren't completely black. Due to weird quantum effects happening just outside the event horizon, they slowly radiate energy away, a faint glow we now call Hawking radiation. This process causes the black hole to gradually lose mass and over eons evaporate completely. The problem is that this Hawking radiation appears to be completely random, pure thermal noise. It contains no information about the intricate details of the matter that originally fell in the stars, planets, or atoms that were consumed. This creates a fundamental crisis. In quantum mechanics, information is always preserved. The state of a system at one time determines its state at all future times. The universe is supposed to be predictable in principle. If a black hole evaporates into a featureless cloud of random radiation, it effectively erases that information from the universe forever. This violation of a core quantum rule is the information paradox. For decades, it pitted the laws of quantum mechanics against the laws of general relativity, with no resolution in sight. The answer, many physicists now believe, lies in entanglement. The secret is that the Hawking radiation particles aren't born alone. Each particle of radiation emitted is intrinsically entangled with a partner particle that falls into the black hole. This creates a complex, evolving web of entanglement connections between the inside of the black hole and the outside universe. As the black hole radiates, this web becomes more and more tangled. The crucial insight is that the information about what fell into the black hole isn't lost. It isn't even inside the black hole anymore. It is somehow encoded in a vastly scrambled and intricate form within the pattern of entanglement relationships between all the Hawking radiation particles that have ever been emitted. Think of it like this. Imagine burning a beautifully detailed, intricate wooden sculpture. The sculpture itself is gone, reduced to ash and smoke. But if you could somehow collect every single atom of that smoke and ash and analyze the exact pattern of their relationships, the precise way the carbon atoms are bonded, the distribution of heat energy among the particles, you could, in theory, reconstruct the original sculpture. The information wasn't destroyed. It was transformed and transferred into the correlations between the particles of the smoke. In the black hole scenario, quantum entanglement provides the threads that weave that correlational tapestry, preserving the information in the radiation itself. This resolution suggests that black holes are not ultimate destroyers, but perhaps the most extreme information processors in the cosmos. Now, let's scale this idea up to a galactic level. At the heart of nearly every large galaxy, including our own Milky Way, resides a supermassive black hole, weighing millions or even billions of times more than our Sun. These colossal entities are not isolated monsters. They are deeply integrated into the life of their host galaxies. They influence how stars form, how gas flows, and ultimately how the entire galaxy evolves. If the physics of stellar mass black holes involves such profound and complex entanglement, what might a supermassive version be capable of? The sheer scale and mass of these objects could allow their quantum properties to persist, even dominate. The event horizon of a supermassive black hole is so vast and its gravity so immense that the process of decoherence, which usually destroys quantum effects, might be suppressed or work differently. The black hole could act as a cosmic anchor for a massive, galaxy-scale quantum state. One provocative possibility is that the supermassive black hole at a galaxy's center could be entangled with the galaxy itself, or even with other galaxies. The intricate web of entanglement that preserves information within the black hole might also extend outward, connecting the black hole to the stars, gas, and dark matter halo that surround it. This could provide a physical mechanism for the strange galactic correlations astronomers observe. The synchronized rotation of galaxies or the aligned jets from supermassive black holes in different galaxies might not be a coincidence. They could be the visible manifestation of this underlying quantum connectedness, with the central black holes acting as the nodes in a vast cosmic network. Furthermore, the process of a supermassive black hole feeding on gas and stars, or merging with another black hole, would be a monumental event in quantum information terms. It wouldn't just be a gravitational spectacle, it would be a massive reorganization of entanglement entropy, potentially sending ripples through the quantum fabric of the entire galaxy, influencing the rate of star formation or the flow of matter in ways we are only beginning to imagine. To grasp how the universe could have gone from a featureless expanse to the structured cosmos we see today, we need to journey back to the very first moments after the Big Bang, to a concept known as cosmic inflation. Picture the newborn universe far smaller than a single atom, filled with an unimaginably dense and energetic field. In a fraction of a second, this field underwent a phenomenal transformation, causing the fabric of spacetime itself to expand faster than the speed of light, smoothing and stretching the entire cosmos. This inflationary period solved many puzzles, like why the universe appears so uniform in every direction we look. But it also left behind a crucial gift, the seeds for all future structure, and those seeds were sown by the quantum world. Even in that primordial, hyper-energy dense state, the universe was not perfectly calm. Due to the fundamental uncertainty principle of quantum mechanics, the inflationary field was subject to tiny, random jitters, minuscule fluctuations in energy that flickered in and out of existence. Under normal circumstances, these quantum fluctuations would be vanishingly small and short-lived. But inflation acted like a cosmic amplifier, stretching these microscopic ripples across the entire sky. Regions that were slightly denser due to a random quantum jitter were stretched into vast, gentle hills of matter and energy, while less dense regions became broad valleys. After inflation ended, gravity got to work on these imprinted wrinkles. The slightly denser regions had a stronger gravitational pull, slowly attracting more and more matter over hundreds of millions of years, eventually collapsing to form the first galaxies, stars, and ultimately, the vast cosmic web we observe today. Every galaxy cluster, every supervoid, can trace its origin back to these quantum fluctuations, blown up to cosmic size. This is where our story of entanglement takes a fascinating turn back to the beginning. The standard model of inflation treats these quantum fluctuations as essentially random, independent events. But what if they weren't entirely independent? What if the same quantum connectedness we've been exploring was already at work, even in that first fleeting moment of creation? The fluctuations that seeded a galaxy in one part of the sky and a galaxy in a completely different part might not have been separate dice rolls. They could have been born from the same quantum state, their fates entangled from the very first moment. This would mean the large-scale structure of the universe, the distribution of galaxies and the voids between them, might not be the result of pure chance, but could instead bear the subtle imprint of a primordial quantum connection. The potential evidence for this lies in the statistical patterns we see in the cosmic microwave background radiation, the ancient afterglow of the Big Bang. This faint light, which fills the entire sky, is a snapshot of the universe when it was just 380,000 years old. The tiny temperature variations in this light, the hot and cold spots, are a direct map of those density fluctuations imprinted by inflation. When cosmologists analyze this map, they look for specific statistical correlations between points on the sky. Some of the patterns they see are exactly what the standard inflationary model predicts. But there have been persistent, intriguing anomalies, strange, large-scale correlations that are slightly stronger than expected. Hints that distant parts of the sky might somehow know about each other in a way that is difficult to explain with purely local physics. These anomalies are the subject of intense debate. Could they be statistical flukes, artifacts of how we measure the data? Perhaps, but they are also exactly the kind of faint signature we might expect if quantum entanglement played a role in shaping the early universe. If the inflationary field was itself a quantum system where different regions were entangled, then the fluctuations it generated would not be completely independent. Their properties would be correlated in a subtle, non-local way, potentially leaving a lasting mark on the arrangement of matter that would eventually form galaxies billions of years later. It's a breathtakingly elegant idea that the spooky links between particles operating in the first instant of time could have dictated the placement of galaxies across billions of light years, weaving a connected cosmos from its very inception. These faint whispers from the dawn of time, the cosmic microwave background, are our most detailed baby picture of the universe. Yet, when scientists stare into this map of the ancient sky, they find a few features that are slightly off. It's like looking at a vast, seemingly random pattern of static on an old television, but then noticing that a few specific shapes keep faintly appearing, patterns that the standard model of cosmology simply cannot explain. One of the most famous is the so-called axis of evil, a strange alignment of certain large-scale features across the sky that seem to hint at a preferred direction in the cosmos, a notion that makes physicists deeply uncomfortable as it challenges the fundamental principle that the universe should look the same in all directions. There are also unusual correlations between the hottest and coldest spots. They appear to be linked in ways that defy the expectation that they should be causally disconnected, having been too far apart at the moment the light was emitted for any influence, even at light speed, to have coordinated them. What if these aren't just statistical glitches or errors in our measurements? What if they are cosmic fossils, the indelible fingerprints of a universe that was born connected? This is where the idea of primordial entanglement offers a stunningly elegant explanation. Remember, the standard story of inflation treats every quantum fluctuation as an independent event. But if the inflationary field itself was a deeply entangled quantum system, then these fluctuations were never truly separate to begin with. Their properties were correlated from birth, their fates intertwined by quantum threads woven into the fabric of space-time itself. Their axis of evil might not be an axis at all, but the visible seam of a vast primordial entanglement between different regions of the early universe. Those strange correlations between distant cold spots could be the lingering echo of a quantum handshake that occurred in the first trillionth of a second of existence, a connection that was then frozen into the fabric of the cosmos by the rapid expansion of inflation and later imprinted onto the light of the cosmic microwave background. This perspective transforms our view of the ancient universe from a collection of separate, random events into a single, coherent, and interconnected quantum system. The anomalies in the background radiation become less like mistakes and more like vital clues, a secret code left behind that we are only now learning to decipher. If this interpretation is correct, it means the connectedness we are potentially seeing between galaxies today isn't a new phenomenon, it's a legacy. It's the continuation of a quantum relationship that was established at the very beginning of everything. The galaxies that appear to be moving in sync or sharing aligned properties aren't just neighbors in a galactic cluster. They are distant cousins whose ancestral lines were quantum-entangled billions of years before they even fully formed. Their shared quantum state is a family heirloom passed down from the primordial fluctuations that eventually gave them birth. Finding definitive proof of this is the monumental task now facing cosmologists. They are developing incredibly sophisticated algorithms to scour the Planck satellite's map of the cosmic microwave background, searching for specific statistical signatures that are the telltale markers of quantum entanglement. They are looking for patterns of correlation that are simply impossible to generate through any classical local process. It's a painstaking search for a needle in a cosmic haystack, but the potential reward is nothing less than a new understanding of reality. Confirming that these anomalies are signs of primordial entanglement would be one of the most profound discoveries in the history of science, providing the first direct observational evidence that the quantum world and the cosmic world are not separate realms, but have been fundamentally linked since the first moment of time. To truly unite the bizarre world of quantum mechanics with the majestic force of gravity, physicists have had to envision frameworks that stretch our understanding of reality to its absolute limit. Two of the most prominent and ambitious of these are string theory and loop quantum gravity, each offering a radically different vision of the cosmos, yet both finding a crucial role for quantum entanglement, especially when we look to the heavens for evidence. String theory proposes that the fundamental building blocks of the universe are not point-like particles but incredibly tiny, vibrating strings. The different vibrations of these strings, much like the various notes on a guitar string, give rise to the different particles and forces we observe. To be mathematically consistent, string theory requires the existence of extra dimensions of space beyond the three we experience, curled up into shapes too small for us to perceive. In this framework, gravity emerges naturally from the vibrations of a specific type of string, the graviton. But how does this connect to entangled galaxies? The answer lies in one of string theory's most profound revelations, the holographic principle and the ER equals EPR conjecture. This suggests that what we perceive as a wormhole, a tunnel through space-time, is actually equivalent to a vast collection of entangled particles. This provides a stunning mechanism for how entanglement could operate over galactic distances. It wouldn't be a signal traveling across space, but information taking a shortcut through the geometry of space-time itself. For a string theorist, the gravitational force holding a galaxy together and the strange correlations we might see between galaxies could all be different manifestations of how these fundamental strings are vibrating and entangling across the hidden dimensions of the universe. Taking a completely different approach, loop quantum gravity does not propose extra dimensions or tiny strings. Instead, it suggests that space itself is not smooth and continuous, as Einstein described, but is actually granular, made of a fabric of tiny, finite loops woven together into a network. Think of it as the universe's underlying pixelation, but instead of square pixels, the fundamental units are these interconnected loops of gravitational field. In this theory, the properties of space, its area and volume are quantized, meaning they come in discrete, tiny packets. Entanglement enters the picture as the glue that connects these individual loops of space. The theory posits that the geometry of spacetime itself emerges from the quantum entanglement between these fundamental units. The strength of the gravitational force between two objects could then be directly related to the amount of quantum entanglement connecting the grains of space between them. This provides a direct and beautiful link between the quantum world and gravity. When we look at a galaxy, its immense gravitational pull could be understood as the collective effect of an astronomically vast network of entangled spacetime quanta. The synchronized behavior of distant galaxies might be a visible signature of this deep, foundational connectivity in the fabric of reality itself. These theories are not just abstract mathematical exercises. They make specific, testable predictions that astronomers can search for, with galaxies acting as the ultimate laboratory. For instance, both frameworks suggest that the nature of spacetime might be subtly different at very small scales or in extreme gravitational fields. This could lead to tiny modifications in how light travels across the universe. By analyzing the light from incredibly distant quasars or gamma-ray bursts that has passed near massive galaxy clusters, scientists can look for signs of this granularity or energy-dependent speed variations, potential smoking guns for these quantum gravity models. Furthermore, the detailed pattern of the cosmic microwave background, the ancient light from the Big Bang, could contain imprints of the primordial quantum fluctuations that seeded galaxies. The specific statistical signatures in this light could tell us whether those fluctuations were truly random or, as these theories might predict, bore the marks of early quantum entanglement. A confirmed detection of such a signature would be a monumental step toward validating one of these frameworks and finally beginning to write the single, unified story of our quantum gravitational universe. But how do we move from these grand, sweeping theories to concrete, testable science? The bridge between mathematical elegance and observable reality is built with the powerful tools of supercomputers and sophisticated simulations. To explore the wild possibility of quantum entanglement influencing entire galaxies, physicists don't just look through telescopes. They run colossal digital experiments, creating virtual universes where they can tweak the very laws of physics to see what happens. These aren't simple video games. They are some of the most complex calculations ever performed, involving billions of particles and the intricate dance of dark matter, gas, and stars, all governed by equations that might include this strange new ingredient: large-scale quantum connectedness. The challenge for any simulation is to take a theoretical concept and translate it into a set of rules that a computer can calculate. For quantum entanglement, this is incredibly difficult. A classical computer, by its very nature, struggles to simulate a truly quantum system because the number of variables explodes exponentially. Simulating even a few dozen entangled particles is a monumental task for today's most powerful machines. So how can we possibly simulate an entire entangled galaxy? The answer lies in a clever workaround. Instead of trying to simulate the entanglement itself at a fundamental level, researchers create phenomenological models. They ask if entanglement were providing an additional force or influencing gravity in a certain way, what would that look like on a galactic scale? They then code this effective influence into their simulations as a new parameter, a subtle tweak to the equations of gravity, and set the universe in motion to see how it evolves compared to a standard model. One of the most compelling areas of study is galactic rotation. In a standard simulation of a spiral galaxy, the stars on the outer edges, without the presence of a dark matter halo, orbit far too slowly. Add the dark matter and the rotation curve flattens out perfectly, matching our observations. But in pioneering studies, scientists have tried a different approach. They've run simulations where they modify the gravitational force law to include a term that acts like an extra attraction, one that doesn't come from additional mass but from something else, a potential signature of an entangled vacuum or other quantum gravitational effect. The results are fascinating. In some of these alternate universe simulations, the rotation curves of the virtual galaxies do flatten out correctly without the need for anywhere near as much dark matter. The simulated stars whip around at the observed speeds, held in place not by invisible matter, but by a modified force arising from the underlying connectedness of space itself. This doesn't prove the quantum idea is correct, but it provides crucial theoretical support, demonstrating that such a model is at least plausible and can replicate one of the key mysteries we see in the real cosmos. The simulations become even more dramatic when they model cosmic collisions, like the future merger between our Milky Way and the Andromeda Galaxy. In a standard gravity-only simulation, such an event is a gravitational ballet, with the galaxies stretching and tearing each other apart over billions of years before finally settling into a new, larger elliptical galaxy. But what if the dark matter halos we believe surround them are not just clouds of particles, but are also regions of enhanced quantum connectivity? Some models suggest that during a merger, this quantum information, this web of entanglement, could itself interact and evolve. The simulation wouldn't just track the motion of stars, it would have to track the flow of quantum information between the merging systems. The resulting galaxy might have a different structure, a different distribution of stars, or even a different rate of new star formation than a classical model would predict. By comparing the outcomes of these advanced simulations to actual telescopic observations of galaxies caught in the act of merging, astronomers can look for anomaly signatures that point toward a more complex, interconnected physics at work. Perhaps the most profound use of these models is in simulating the universe's large-scale structure, the cosmic web of filaments, clusters, and voids that defines the modern cosmos. The standard model, using cold dark matter and the cosmological constant, does a remarkably good job of replicating the web we see. The question for quantum models is whether they can do just as well or perhaps even better. Teams of researchers are now running massive cosmological simulations that start with the initial conditions from the cosmic microwave background and then evolve forward in time using modified gravity laws inspired by quantum entanglement ideas. They are looking to see if their virtual universes produce the same statistical distribution of galaxy clusters, the same sizes of voids, and the same subtle correlations between distant structures. A successful match wouldn't just be a curiosity, it would be a monumental step forward, suggesting that the same quantum principle that governs the behavior of particles could also be the invisible architect that designed the entire universe. These digital universes are our testing grounds, our portals into possibilities beyond our current understanding, allowing us to peer into a reality where the cosmos is not a collection of separate objects, but a single, deeply interconnected quantum whole. So what would this cosmic quantum connection actually look like through the lens of a telescope? If entangled galaxies are out there, they wouldn't be flashing neon signs. We'd need to know exactly what subtle, statistical anomalies to search for in the vast sea of data. One of the most promising signatures is the phenomenon of correlated spins. When astronomers measure the rotation of spiral galaxies, they note both the direction clockwise or counterclockwise and the tilt of their spin axes. In a universe governed purely by local gravity and random chance, you'd expect these spins to be completely uncorrelated, like a vast crowd of people all turning in random, independent directions. But several studies have reported a peculiar finding. Galaxies separated by tens of millions of light years appear to show a slight but statistically significant preference for their axes of rotation to be aligned with each other. It's as if these island universes, which should have no way to communicate, are somehow synchronizing their pirouettes across the void. This kind of coordination is incredibly difficult to explain with standard gravitational models alone, but it's precisely the kind of instantaneous, non-local correlation that quantum entanglement provides a natural mechanism for. Beyond their spin, astronomers are also looking for synchronization in the very life cycles of galaxies. Consider the activity of their central supermassive black holes. When these behemoths feed on surrounding gas, they can become active galactic nuclei, shooting out colossal jets of energy. Now, imagine finding two such active galaxies separated by a vast distance that appear to flare up and quiet down in an eerily synchronized pattern. The timing of these energetic outbursts would be the key. If the pattern of activity is so tightly correlated that even a signal traveling at the speed of light couldn't have communicated between them in the time since the universe began, it would point toward a connection that transcends spacetime itself, a hallmark of quantum entanglement. Similarly, the rate of star formation within galaxies could serve as another cosmic heartbeat. If two galaxies with no apparent gravitational link are found to have simultaneous, massive waves of star birth or periods of quiescence, it could suggest their interstellar gases are responding to a shared, non-local influence, as if an invisible thread is pulling on the triggers of their cosmic evolution in unison. To move from intriguing hints to definitive proof, we need more than just statistical curiosity. We need next-generation observatories with the precision to map the universe in unprecedented detail. The upcoming Vera C. Rubin Observatory, scheduled to begin its legacy survey of space and time in a few years, will be a game-changer. This monumental project will image the entire visible sky every few nights for a decade, creating an ultra-deep time-lapse movie of the cosmos. This incredible dataset will allow astronomers to measure the properties of billions of galaxies, their shapes, spins, and activities, with a statistical power never before possible. It will be the ultimate tool for hunting down those subtle, large-scale correlations that could betray the presence of quantum connectedness. By applying sophisticated machine learning algorithms to this ocean of data, scientists will be able to search for the faintest whispers of synchronized behavior that current telescopes simply cannot see. Looking further into the future, space-based missions will take this search to even greater extremes. The European Space Agency's planned Athena X-ray Observatory will peer deep into the hearts of galaxies to study the feeding habits of supermassive black holes with incredible accuracy, potentially catching them in the act of synchronized flaring. Even more ambitious concepts are on the drawing board, like a future gravitational wave observatory based in space, such as the Laser Interferometer Space Antenna. While its primary goal is to detect ripples in spacetime from merging black holes, its exquisite sensitivity could also be used to probe the fundamental nature of spacetime itself, potentially revealing whether its texture is smooth or granular, a key prediction of some quantum gravity theories that rely on entanglement. Each new telescope and mission brings us a step closer to viewing the universe not as a collection of isolated islands, but as a single, interconnected quantum network where the behavior of one galaxy is a silent testament to the state of another, billions of light years away. Of course, the scientific journey toward accepting such a radical idea is paved with healthy skepticism and formidable challenges. The most significant hurdle by far is the colossal problem of decoherence. We know from countless laboratory experiments that maintaining a quantum state is a delicate balancing act, like trying to keep a house of cards standing in a breeze. The moment a quantum system interacts with its environment, be it a stray photon, a passing molecule, or even the faint warmth of its surroundings, that fragile, interconnected state collapses into a definite classical reality. This process happens almost instantaneously for objects we can see and touch. So, the idea that an entire galaxy, a chaotic maelstrom of hundreds of billions of stars, swirling gas, dust, and radiation, could somehow preserve a coherent quantum state for billions of years seems, to many physicists, almost laughably impossible. The environmental noise within a galaxy is unimaginably loud. It should shred any delicate quantum connection to pieces the moment it tries to form. Proposing large-scale entanglement is, in essence, suggesting that a symphony orchestra could play a perfect, synchronized melody while each musician is sealed inside their own separate roaring hurricane. Beyond the theoretical challenge, there's the immense practical difficulty of testing these ideas. How do you design an experiment to prove that two galaxies a billion light-years apart are quantum entangled? We can't exactly put them in a lab, isolate them from their environment, and run a Bell test. Any evidence we gather is purely observational and statistical, gleaned from painstakingly analyzing the light that has traveled across the cosmos to reach our telescopes. This introduces a host of potential pitfalls. The correlations we might attribute to quantum entanglement could very easily be caused by more mundane, classical astrophysical processes that we simply haven't thought of or don't fully understand yet. For instance, perhaps galaxies that appear synchronized were born from the same vast filament of dark matter in the early universe, and their similar spins are just a fossil relic of that common origin, a gravitational influence that acted locally billions of years ago. This is the classic scientific dilemma. Correlation does not imply causation. Finding a pattern is one thing. Proving it can only be explained by a specific, exotic quantum mechanism is another thing entirely. This leads directly to the core of the skepticism within the scientific community. Many researchers argue that before we invoke radical new physics like cosmic scale entanglement, we must first exhaust all possible explanations within our current, well-tested frameworks. The standard model of cosmology, with its dark matter and dark energy, has been spectacularly successful at explaining the large-scale structure and evolution of the universe. While these components remain mysterious, they provide a coherent, mathematically sound model that fits a vast array of data. Proposing that quantum entanglement could account for some dark matter effects or galactic correlations is often viewed as adding an unnecessary layer of complexity. The principle of Occam's razor that the simplest solution is often the best suggests we should first try to find the missing particles of dark matter or understand the nature of dark energy before we tear down and rebuild the entire foundational understanding of how gravity and quantum mechanics interact on cosmic scales. Furthermore, there is a significant philosophical resistance. The idea of entanglement influencing galaxies can, if not carefully presented, veer dangerously close to sounding like mysticism or panpsychism. The idea that consciousness or connection is a fundamental property of the universe. Most physicists are deeply committed to a materialistic, reductionist view of reality, where large-scale phenomena emerge from the collective behavior of small-scale parts following well-defined local rules. The concept of spooky action at a distance affecting entire galaxies feels, to some, like a step away from that rigorous framework back toward a more magical, pre-scientific worldview. This isn't a trivial objection, it's a fundamental difference in approach to how we believe the universe should operate. For these theories to gain broader acceptance, they must not only provide compelling mathematical models and observational evidence, but also a convincing physical mechanism that explains how such massive decoherence avoidance is possible, moving the idea from the realm of fascinating speculation into the domain of testable, predictive science. This rigorous challenge is not a dismissal but an essential part of the process, ensuring that any eventual paradigm shift is built on a rock-solid foundation of evidence and reason. But if we can begin to unravel these cosmic quantum connections, the technological implications are nothing short of revolutionary, offering possibilities that leap straight from the pages of science fiction into the realm of future engineering. The most immediate and profound application lies in the realm of communication. Our current methods for talking across the solar system are frustratingly slow. A signal from Mars can take up to 20 minutes to reach Earth, making real-time conversation with astronauts or control of distant rovers an impossible dream. A network built on the principles of quantum entanglement could change everything. Imagine a series of satellites, each carrying a bank of entangled particles, positioned from Mercury to the outer reaches of the Kuiper belt. If we can create and preserve these entangled links, we could establish a solar system-wide web allowing for instantaneous communication. The moment a particle on a probe near Pluto is measured, its entangled partner on Earth would reflect that state change immediately, bypassing the light speed delay entirely. This wouldn't just be a faster phone call home. It would enable the precise, real-time navigation of swarms of drones mapping the oceans of Europa, or the construction of vast orbital infrastructure around Jupiter, all coordinated from mission control on Earth without a single second of lag. This leap forward in connectivity could fundamentally alter our relationship with space exploration, but the potential extends far beyond mere communication. The same principles that might bind galaxies together could inspire a new generation of propulsion technology, offering a potential solution to the greatest hurdle of interstellar travel, the sheer mind-numbing distance between stars. Conventional rocketry is utterly inadequate for such journeys. A voyage to the nearest star system, Alpha Centauri, would take tens of thousands of years with our current technology. Theories that link entanglement to the fabric of spacetime itself, like the ER=EPR conjecture suggesting wormholes are built from quantum connections, open a tantalizing door. If a wormhole is essentially a manifestation of entanglement, then perhaps we could learn to engineer or stabilize these spacetime shortcuts. Instead of burning propellant to cross 4.3 light-years, a spacecraft might traverse a created or discovered wormhole, effectively taking a topological shortcut through the universe. While building an interstellar tunnel remains a monumental challenge far beyond our current capabilities, understanding the quantum mechanics that could underpin it is the essential first step. It transforms the concept from pure fantasy into a distant, but physically plausible engineering goal, a future where we don't fly between the stars, but step through a quantum door to arrive instantly. The impact of this knowledge wouldn't be confined to the depths of space. It could also lead to a radical transformation of energy generation and distribution here on Earth. If the vacuum of space truly is a seething, entangled energy field as some models suggest, then we might one day learn to tap into it. This isn't about violating conservation laws, but about understanding how to interact with this quantum substrate in a controlled way. The goal wouldn't be to create a perpetual motion machine, but to develop a technology that could draw upon the ubiquitous zero-point energy of the universe itself. Furthermore, the management of energy on a planetary scale could be revolutionized by quantum sensing networks. Ultra-precise quantum gravimeters, whose accuracy is protected by entanglement, could map the Earth's subsurface in exquisite detail, locating geothermal vents and mineral deposits with unprecedented precision, optimizing our energy extraction and reducing environmental impact. A deep understanding of cosmic-scale quantum effects could provide the manual for interacting with the fundamental energy of the universe, moving us from an era of resource extraction to one of subtle, universal resonance. Perhaps the most transformative application of all would be in the realm of computation. Our current efforts in quantum computing are heroic battles against decoherence, trying to protect fragile qubits from the noisy outside world long enough to perform a calculation. But if the universe itself can maintain quantum states on a galactic scale for billions of years, it means there are natural, cosmic-scale mechanisms for suppressing decoherence that we have yet to discover or understand. Studying how the quantum vacuum remains coherent across light years could provide the foundational insights needed to build robust, large-scale quantum computers here on Earth. We might learn to engineer materials that mimic the structure of space-time itself, creating qubits that are inherently stable. A computer built on such principles could model complex systems, from global climate patterns to the molecular dynamics of new life-saving drugs, with an accuracy that is simply unattainable today. The processing power needed to simulate the very cosmic entanglement that inspired it would finally be within our grasp, launching a virtuous cycle of discovery and technological advancement that would redefine the limits of human knowledge and capability. The notion that galaxies might be quantum entangled doesn't just challenge our physics, it upends our entire philosophical understanding of reality and our place within it. For centuries, we've viewed the cosmos as a vast, mostly empty stage, with celestial objects as isolated actors following a script written by impersonal forces like gravity. We are mere spectators on a tiny rock, separate from the distant lights in the sky. But what if that stage itself is an illusion? What if the actors, separated by unimaginable voids, are fundamentally linked, performing a coordinated dance directed by a deeper, invisible connection? This shifts our perspective from a universe of separation to a universe of profound, intrinsic relationship. It suggests that isolation might be the grand illusion, and that at the most fundamental level, everything is in conversation with everything else. Our very sense of being a solitary observer, a tiny self-aware speck in a cold, uncaring void, could be a limited perception, a story we tell ourselves because we cannot yet see the threads that bind our star to all others. This cosmic connectivity forces us to reconsider the very nature of existence and consciousness. If the universe is indeed a single, interconnected quantum system, then the emergence of life and mind might not be a random, isolated accident in a remote corner of space. Instead, it could be a natural expression of the universe becoming aware of itself. Our consciousness, our ability to observe and ponder these mysteries, might be a localized manifestation of a universal tendency toward awareness, woven into the fabric of reality through the same quantum connections that link the galaxies. We are not just living in the universe, we are the universe experiencing itself, and the entangled galaxies are a mirror reflecting our own deep connection to the whole of existence. This idea resonates with ancient philosophical and spiritual traditions that have long spoken of the unity of all things, the web of life, the concept of an underlying oneness. Modern physics, in its quest for the most fundamental description of reality, might be stumbling upon a scientific validation of this timeless intuition, suggesting that the separation between the spiritual and the scientific might itself be another illusion waiting to be dissolved. Ultimately, this journey into the heart of cosmic entanglement invites a profound sense of humility and wonder. It reveals that our current understanding of reality, no matter how advanced, is likely still a crude sketch of a far more magnificent and mysterious masterpiece. The universe is not merely stranger than we imagine, it is stranger than we can imagine. Each time we peel back a layer, we find greater complexity, deeper beauty, and more bewildering questions. The possibility of entangled galaxies is a humbling reminder that we are still at the very beginning of a grand cosmic adventure of discovery. It encourages us to remain curious, to embrace the unknown, and to continue looking up at the stars not just as distant points of light, but as potential partners in a silent, billion-year-old quantum conversation, a conversation that we are only now learning how to hear. Long before physicists ever put pen to paper to calculate the probability of quantum connections on a cosmic scale, storytellers and dreamers were already imagining a universe bound together by invisible threads. The human imagination has a remarkable way of anticipating scientific frontiers, and the concept of a deeply interconnected cosmos is a powerful theme that has resonated through science fiction for generations. This genre hasn't just entertained us, it has provided a cultural and emotional language for grappling with these profound ideas, long before we had the mathematics to describe them. Think of the iconic Ansible from Ursula K. Le Guin's novels, a device that allowed for instantaneous communication across light years, defying the limitations of light speed. Le Guin didn't need to call it quantum entanglement. She understood the human desire for connection and the narrative power of a universe where distance is no barrier to conversation. Her invention wasn't just a plot convenience, it was a philosophical statement about community and understanding in a vast cosmos, giving us a fictional model for the very kind of connectedness physicists are now exploring. This theme of cosmic networking finds perhaps its most spectacular expression in the concept of a galactic community. From the sprawling empires of Isaac Asimov's Foundation series to the diverse alien federation in Star Trek, science fiction has consistently envisioned our galaxy not as a collection of isolated star systems, but as a single, interconnected political and social entity. The very premise of these stories requires a level of communication and travel that bends or breaks the known laws of physics, but that creative liberty allows them to explore the implications of a truly unified cosmos. How would different species interact if they could meet as easily as neighbors across a street? What shared laws or ethics would emerge from a reality where everyone is fundamentally connected? These narratives serve as a grand thought experiment, allowing us to play with the social, political, and ethical consequences of a universe where the tyranny of distance has been overcome, mirroring our own scientific curiosity about whether such a physical connection might actually exist. The silver screen has brought these ideas to life with breathtaking visuals that sear the concept of cosmic unity into our collective consciousness. The stunning climax of the film Contact, based on Carl Sagan's novel, provides a powerful metaphor. When Dr. Ellie Arroway travels through a series of wormholes, she doesn't just journey to another star. She experiences the universe as an intricate, woven tapestry, a place of breathtaking beauty and profound connection. The sequence, though fictional, evokes the feeling of the holographic principle or the ER equals EPR conjecture, the sense that the universe is a carefully constructed network and that every point is intimately related to every other point. Similarly, the interdimensional portal in Interstellar, while rooted in speculative gravitational physics, visually represents the idea of a hidden architecture to the cosmos, a structure that allows for navigation beyond our conventional 3 dimensions. These moments in cinema do more than just dazzle us. They make the abstract tangible, providing an emotional and visceral understanding of concepts that equations alone cannot fully convey. Perhaps the most direct and poignant exploration of this idea is found in the phenomenon of spice agony from Frank Herbert's Dune. The Guild navigators use the spice melange to expand their consciousness, allowing them to perceive safe pathways for travel through folded space. This is more than just psychic power. It's a fictional representation of accessing a deeper layer of reality, a quantum landscape where points that are distant in normal space are adjacent. The navigators don't compute a route, they feel the connection, embodying the idea that the universe's true structure is not geometric but relational. This brilliantly mirrors the scientific proposition that entanglement might define the very geometry of space-time. Herbert's genius was in linking this cosmic perception to a transformative and even terrifying human experience, suggesting that truly understanding the universe's connected nature would fundamentally change who we are. This rich history of science fiction serves a crucial purpose beyond entertainment. It acts as a cultural and psychological primer, preparing our minds to accept possibilities that might otherwise seem too strange or counterintuitive. When a physicist today talks about entangled galaxies or a holographic universe, these concepts land on a culture that has already been seeded with similar ideas for decades. The imaginative work of authors and filmmakers has built a bridge, allowing the public to cross more easily from the world of classical physics into the bewildering world of quantum cosmology. The stories provide the analogy, the metaphor, and the emotional hook that makes the cold, hard science not just comprehensible but compelling. They remind us that at the heart of every equation is a fundamentally human story about our place in the cosmos, a story of longing to understand, to connect, and to find that we are not alone in the vast, silent dark, but part of a grand and mysterious whole. This incredible convergence of theoretical speculation and observational pursuit is now being forged into a formal scientific endeavor through ambitious interdisciplinary collaborations. The hunt for evidence of cosmic quantum connections is no longer a fringe interest. It's becoming a mainstream mission that brings together cosmologists who map the heavens, quantum information scientists who understand entanglement, and particle physicists who probe the fundamental laws. Major institutions like the Perimeter Institute for Theoretical Physics in Canada and the Simons Foundation in the United States are now hosting dedicated workshops and funding research programs explicitly focused on quantum gravity and entanglement in the cosmological context. These gatherings are melting pots of ideas where an expert in building quantum computers might share coffee with an astrophysicist who studies the clustering of galaxies, each learning the other's language to ask a better question of the universe. One of the most exciting near-term projects is the full analysis of data from the Vera C. Rubin Observatory's legacy survey of space and time. This isn't just one experiment, it's a global research program. Teams around the world are developing sophisticated machine learning algorithms right now, training them to sift through the billions of galaxies the LSST will catalog, searching for those subtle statistical anomalies, the unusual alignments and synchronized behaviors that could be the hallmark of entanglement. They're creating detailed simulations of what the universe should look like without these effects, creating a null hypothesis baseline. Any significant, persistent deviation from that baseline in the real data could be the first solid clue. Another key initiative involves using the James Webb Space Telescope not just to look at the earliest galaxies, but to study their properties in unprecedented detail. By analyzing the polarization of light from these ancient objects and looking for correlated patterns across the sky that have no business being connected, researchers hope to find a fossilized imprint of primordial quantum connectedness. Looking further ahead, the quest will move from looking at light to listening for the ripples in spacetime itself. The planned Laser Interferometer Space Antenna, a future gravitational wave observatory, will open an entirely new window. While its primary goal is to detect low-frequency gravitational waves from merging supermassive black holes, its data could also be used to perform our ultimate test. By comparing the timing of signals arriving at the three LISA spacecraft, physicists could probe the fundamental nature of spacetime, searching for signs of a quantum foam or granularity that is predicted by theories where entanglement builds the geometry of the universe. If spacetime is smooth, as Einstein believed, the signals will behave one way. If it has a quantum structure built on entanglement, the signals could show a very different telltale signature. For anyone captivated by this journey and eager to follow along as these discoveries unfold, staying informed is easier than ever. You don't need a PhD to track the progress. Prestigious scientific journals like Physical Review, Letters, Nature, and Science often publish the biggest breakthroughs, and their press release sections offer excellent summaries written for a general audience. Following the social media accounts and blogs of major research institutions like CERN, NASA, the European Space Agency, and the Max Planck Institute can provide direct updates. For deeper dives, open access online repositories like arXiv.org are where physicists from around the world post their preliminary research papers daily, completely free to read. It's a raw feed of the scientific process, allowing you to witness ideas the moment they are proposed and debated by the global community. The story of entangled galaxies is still being written, and we all have a front row seat to what may be one of the most profound paradigm shifts in our understanding of reality. While the idea of galaxies whispering to each other across the void feels like the stuff of far future science, the pursuit of this knowledge is already sending ripples back to Earth, poised to revolutionize the technology we use every single day. This isn't just about understanding the cosmos, it's about learning its deepest secrets to rewrite the rules of engineering here on the ground. The most immediate impact is happening in the race to build a practical quantum computer. Right now, the biggest obstacle is decoherence, preventing the delicate quantum bits or qubits from collapsing into ordinary bits due to the slightest environmental noise. It's an epic battle to isolate these systems, keeping them colder than deep space and shielded from every stray vibration. But if the universe itself can maintain quantum states across light years within the chaotic environment of a galaxy, it means nature has already discovered powerful methods of error correction and coherence protection that we have yet to imagine. By studying the theoretical models that allow for large-scale entanglement, scientists are gaining crucial insights into how to design qubits that are inherently more robust. This could lead to new materials or quantum error-correcting codes inspired by the cosmos itself, ultimately bringing large-scale, stable quantum computing out of the lab and into reality, transforming everything from drug discovery to climate modeling. This cosmic inspiration extends beyond computing into the very way we might generate and manage energy. One of the most speculative yet thrilling possibilities involves the quantum vacuum itself. If the empty space between stars is indeed a seething, entangled energy field, as some models suggest, then understanding its structure could be the key to unlocking entirely new forms of power. This isn't about creating energy from nothing, but about learning to interact with this fundamental substrate of reality in a controlled way. Think of it like the first humans who learned to harness flowing water with a wheel. They didn't create the river, they simply tapped into a natural, pervasive energy flow. A deep understanding of the entangled vacuum could one day lead to technologies that interact with this zero-point energy field, potentially providing a virtually limitless and ubiquitous power source. Furthermore, the advanced materials needed to detect such subtle cosmic effects will inevitably trickle down. Ultra-sensitive quantum sensors, developed to hunt for the faint signatures of entangled galaxies, could be deployed to map geothermal energy reservoirs beneath our feet with pinpoint accuracy, or to monitor the health of our power grids with unprecedented precision, preventing blackouts and optimizing distribution. Perhaps the most tangible future application lies in navigation and communication. Our current global positioning system is incredible, but it relies on a fleet of satellites and can be easily disrupted. Now, imagine a future navigation system that doesn't look up to the sky, but down into the fabric of the Earth itself. By placing ultra-precise quantum gravimeters devices that measure tiny fluctuations in gravity throughout the planet's crust, we could create a stable, unmovable, and utterly reliable positioning network. These devices, whose accuracy is protected by quantum principles, would create a unique gravitational fingerprint for every location on Earth. Your phone or car would navigate by feeling the subtle pull of the rock beneath it, a system that would work everywhere from the deepest ocean trench to the most remote mountain range, completely independent of satellites and immune to jamming or spoofing. And for our dreams of becoming an interplanetary species, this knowledge is absolutely essential. The same principles that might allow for cosmic-scale entanglement could enable a solar system-wide quantum internet. We're already laying the groundwork for this on Earth, with networks that use entangled photons to create perfectly secure communication links. Scaling this up using satellites could create an unhackable web connecting future colonies on Mars, mining outposts in the asteroid belt, and research stations on the moons of Jupiter. This wouldn't just be about faster videos from Mars. It would enable real-time, lag-free control of remote machinery and complex, coordinated scientific endeavors across the entire solar system, turning a collection of outposts into a truly connected interplanetary civilization. The journey to understand the universe's deepest connections is therefore also a journey to build a better, more advanced and more interconnected future right here at home. Now, I want to turn the microphone over to you for a moment. Let's try a little thought experiment together. Close your eyes and picture this. It's the year 2274, and humanity has become an interstellar species. We have thriving colonies scattered across dozens of star systems. But here's the twist: our entire understanding of physics has been rewritten. We've confirmed that quantum entanglement is a real, tangible force connecting celestial bodies across the cosmos. So I pose this scenario to you. You're the chief science officer on a starship venturing into a region of space where two distant galaxies are known to be profoundly entangled. What unfolds on your journey? Does your ship's navigation system suddenly glitch, calculating impossible shortcuts between stars that shouldn't be linked? Do your long-range sensors pick up identical patterns of solar flares happening simultaneously in both galaxies, as if they're mirroring each other across the void? And most intriguingly, imagine if your ship's experimental quantum communication array, designed to send messages using entangled particles, suddenly starts receiving a coherent signal, not from your intended recipient on Earth, but from a source somewhere within that entangled galactic pair, a signal that seems to respond instantly, defying every law of conventional physics. How would that change your mission? Would you attempt to respond? What would you even say? This isn't just science fiction. It's a doorway into the practical implications of the science we've been exploring. If the fabric of reality is woven with these quantum threads, then the future of exploration, communication, and even our place in the universe shifts dramatically. Think about our current struggle with the speed of light, that absolute cosmic speed limit that makes a simple conversation with someone on Mars a 20-minute exercise in patience. If galactic-scale entanglement is real, it hints at a universe where information, or perhaps even influence, doesn't have to plod along at light speed. It could mean that the cosmos has a built-in, instantaneous networking protocol we're only beginning to detect. This could revolutionize everything. Spacecraft wouldn't just be charting courses through empty space. They might be mapping currents and eddies in a flowing river of quantum connectivity, seeking out natural entanglement corridors that act as cosmic shortcuts. I'm incredibly curious to hear what you think. Drop your ideas in the comments below. Tell me how you think a confirmed connection between galaxies would reshape human civilization. Would it bring us closer together, knowing that vast distances might be an illusion? Or would it present terrifying new challenges, perhaps revealing that we're not the only ones who might learn to use this network? Let's get a discussion going. Share your most creative scenarios for space travel, your visions for instantaneous communication, or your thoughts on what we might discover lurking in those quantum links. Your perspective is a vital part of this ongoing conversation, and who knows, the idea you share today might just foreshadow the discovery of tomorrow. Today we've journeyed across an incredible landscape of ideas, From the spooky connections between particles in a lab to the breathtaking possibility that entire galaxies might be whispering to each other across the cosmos. We started with the basics of quantum entanglement, that strange but proven phenomenon where particles become linked so completely that affecting one instantly affects its partner, no matter the distance. We saw how this defied even Einstein's expectations, earning the name spooky action at a distance, and how decades of painstaking experiments from labs to satellites have confirmed it's a fundamental feature of our reality. This journey took us to the heart of physics' biggest problem, the glaring divide between the quantum world, ruled by probability and connection, and the cosmic world described by Einstein's gravity. For a century, these two sets of rules have been incompatible, but the audacious idea of cosmic entanglement might just be the bridge that finally connects them. We explored how the seeds for this radical connection might be sown by theories like quantum gravity and string theory, which suggest that the very fabric of space-time could emerge from a vast, underlying network of quantum entanglement. The ER equals EPR conjecture gave us a stunningly elegant image. A wormhole, a tunnel through the universe, might not be so different from a pair of entangled particles. This implies that what we perceive as empty space is anything but. It could be a vibrant, dynamic quantum vacuum, a seething sea of energy whose structure is defined by these invisible threads. This perspective offers a revolutionary new way to look at the universe's greatest mysteries. The gravitational glue we call dark matter, which holds galaxies together, might not be an invisible substance but a manifestation of this entangled vacuum's curvature. Similarly, the mysterious dark energy accelerating the expansion of the cosmos could be understood as the energy inherent in this connected void. Then we looked for proof, turning our gaze to the heavens to find galaxies that seem to move in impossible sync, their spins aligned or their black holes flaring in unison across millions of light years. These cosmic anomalies, these faint whispers of coordination, could be the observable echoes of a quantum connection established at the dawn of time, perhaps even imprinted in the ancient light of the cosmic microwave background. We confronted the colossal challenge of decoherence, the reason we don't see quantum weirdness in our daily lives, and wondered if the universe itself, in its vast, cold emptiness, might provide the perfect sanctuary for these effects to persist on a monumental scale. This isn't just a minor tweak to physics, it represents a complete paradigm shift. It suggests a universe that is not a collection of separate objects but a single, deeply interconnected system. A cosmic hologram where the information for everything is woven into the fabric of reality itself. If these theories hold, the implications are profound, reaching far beyond academic journals. It would mean rewriting our textbooks and our understanding of reality from the ground up. We would have to accept that the universe is fundamentally non-local, that separation is an illusion, and that everything is in a silent, instantaneous conversation. This new cosmology would not only solve lingering puzzles about dark matter and dark energy, but could also open doors to technologies that sound like science fiction. Lag-free communication across the solar system, navigation systems that use the planet's gravitational fingerprint, and perhaps one day, a deeper understanding that allows us to interact with the universe's quantum substrate itself. This is more than a new chapter in physics. It's a potential revolution in our cosmic story, transforming us from isolated observers on a tiny rock into active participants in a deeply entangled, conscious, and truly unified cosmos. And so we find ourselves standing at the edge of a truly new cosmic paradigm, peering into a universe that is far more mysterious and deeply unified than we ever dared to imagine. This journey from the spooky links between particles to the potential whispers between galaxies isn't just a tale of scientific discovery. It's a profound shift in how we see our place in the grand scheme of things. We are not merely inhabitants of a vast, empty space, but possibly active participants in a cosmic network of connection. a living tapestry woven with threads of quantum information that bind everything from the smallest atom to the largest cluster of galaxies. This vision of an entangled cosmos invites us to reconsider the very nature of existence, suggesting that the distances which seem to separate us are, in a fundamental sense, an illusion, that we are all, in ways we are only beginning to understand, part of a single, breathtaking whole. The pursuit of this knowledge is a testament to the relentless curiosity of the human spirit. For centuries, we have looked up at the night sky with wonder, asking questions that seemed impossible to answer. Today, we are developing the tools and the theories to actually begin answering them, to test these grand ideas against the reality of the cosmos itself. It's a challenging, often controversial, and always thrilling endeavor, one that requires us to be both rigorously skeptical and boldly imaginative. Whether the evidence ultimately confirms that galaxies are entangled or leads us down another unexpected path, the very act of asking these questions expands the boundaries of human understanding and brings us closer to comprehending the true nature of the reality we all share. This story is far from over. In many ways, it is just beginning. The next decade promises a flood of new data from powerful telescopes and satellites, each observation offering a potential clue, a piece of the puzzle that could either solidify this new paradigm or send us back to the drawing board. That's the beautiful, dynamic process of science. It's a conversation with the universe, one where we must listen carefully and be willing to be surprised. Your engagement with these ideas is a vital part of that conversation. Your curiosity, your questions, and your sense of wonder fuel the collective drive to explore and understand. If this journey through the possibilities of a quantum-connected universe has sparked your imagination, I urge you to stay curious. The greatest discoveries often lie just beyond the edge of what we currently know. Please like this video if you enjoyed the exploration, and subscribe to the channel to join us as we continue to investigate the biggest mysteries of science and existence. This is a conversation I deeply want to continue with you. Let me know in the comments below, do you think it's possible that galaxies could be entangled? What aspect of this cosmic connection fascinates or baffles you the most? Share your thoughts, your own theories, and let's keep looking up at the stars together, forever marveling at the profound and beautiful interconnectedness of it all.